So in the previous video, I talked just a little bit about the basic binomial distribution. And in this video, I want to dig a little bit deeper into what the expected value is on a binomial distribution. And the formula for the expected value is intuitive, but the proof of it is a little bit tricky. So I want to show you how to go through both of those. But I want to start with just a simple question. If you flip a coin 100 times, what's the average number of heads that you're going to get? Well, many people can do that problem pretty easy. Okay, flip a coin 100 times, 50% chance of getting a heads. So you're thinking that the expected number of heads is just going to be 50% of 100. And then you're going to say 50. And that makes sense. Let's say that you were rolling a die. Let's say you're rolling a die 60 times and you wanted to know the expected number of sixes that you're going to get. Well, you're going to say, okay, a sixth of the numbers are a six, and I rolled it 60 times, so you're thinking 10 die. So this is a very intuitive formula, and what you're thinking is that if you have a binomial distribution where there are n trials that are happening, and there's a p chance of the thing you care about happening, then you would think intuitively your expected value is going to be just n multiplied by p. It turns out that this is the correct answer. But I want to show you, going through straight from the definition of the binomial distribution, how you can prove that this is actually true for all binomially distributed variables. So let's hold that in mind. Oops, I'm hitting the wrong buttons. Hold that in mind. So what we know is two things. We know that the expected value in general, this is not just for binomial, but the expected value for any discrete variable is the sum over all the outcomes of x multiplied by the probability that your random variable equals x. And we know that with a binomial variable, the probability that x is equal to x is equal to n choose, here, let's make this x is equal to a certain k value, is the probability of n choose k times p to the k 1 minus p to the n minus k. And so we're going to put those two things together. I guess I could use the same x value on both of those, just to, let's make those k's all into x's. Okay. So what we're going to do is put these two ideas together. That means that the expected value for a binomial distribution looks like this. The sum over all x's of x times the probability that we reach x and choose x, p to the x, 1 minus b to the n minus x. What I'm going to do is write out the first couple terms and then throw a dot, dot, dot on there, just so you can kind of see the pattern. The first possibility is 0, that you flip a coin a bunch of times, you get 0 heads, or you get 0 sixes on it. So the first possibility is 0 times n choose 0, p to the 0, 1 minus p to the n. Not a lot interesting happening there. The next possibility is 1 times n choose 1, p to the 1, 1 minus p to the n minus 1. The next possibility is 2 times n choose 2, p to the 2, 1 minus p to the n minus 2, etc., etc., etc. All the way up to the very last possibility is that you get all heads, or you get all successes. So we have n times n choose n times p to the n times 1 minus p to the n minus n. So there's a lot of stuff that actually cancels out and simplifies here. So first thing I want to do is let's just cross off the 0 term, because that's all equal to 0 anyway. And then the other thing that's gone is n minus n is 0, which means this 1 minus p is really just 2 at the first power. So what I want you to notice now is that every other term has a p in it. And every other term has some sort of n choose something on it. So I'm going to remind you, just a quick sidebar, that if we have n choose k, we can write n factorial over k factorial n minus k factorial. So I'm going to write out our sum again in a slightly different format. So we've got n factorial over n minus 1 factorial times p times 1 minus p to the n minus 1. Oops, I shouldn't have put plus at the beginning. I should have put equals. Okay, I accidentally cleared the screen, so we'll fix it. So equals. This is my n choose 1. And then I have p to the 1. 1 minus p to the n minus 1. Then I have 2 times n choose 2. P squared 1 minus p to the n minus 2. All the way up to n times n choose n minus n factorial, p to the n. So every term now, you can see how they all have a p in common, and you can see that they all have an n in common. So I can factor those out, n and p. And then let's write out what's left over. If I borrow an n from the first term, then I have n minus 1 factorial over n minus 1 factorial. And I pulled the p out, so it's times p to the 0, 1 minus p to the n minus 1. I could have written 1, but I'll explain in a second why I wrote p to the 0. Then, if you pull out an n and a p, you can also cancel 2 over 2 factorial to have n minus 1 factorial over n minus 2 factorial, p squared, but I took out one of the p's, so I have p to the first, 1 minus p to the n minus 2, plus dot dot dot. If I pull out an n and a p here, then I'm left with n factorial over, actually I'm going to do that slightly differently, because I want my tops to match as n minus 1s. So let's write that slightly differently. What I'm going to do is, just like the 2 factorial canceled the 2 here, and in the next term there would be a 3 and a 3 factorial, which you can cancel out to make this into 2 factorial on the bottom. Here what I'm going to do is take this n and make this into an n minus 1 factorial. So I have n minus n factorial, n minus 1 factorial, and I'm going to pull another n out to make this n minus 1 factorial on the top, p to the n minus 1. Now, it might take a little bit of imagination to see what's happening here. All of the terms on the right now can be written as some sort of a sum. And the sum goes from k equals 0 up to n minus 1. The term in the front is always n minus 1. Is that right? Yeah, n choose k. So it's always n minus 1 factorial. And then on the bottom, we have n minus 1 minus k factorial and k factorial. So what I'm saying is, when in the 0th term, we could put a 0 factorial right here. This is my first term. I could put a 1 factorial. In the second term, I could put a 2 factorial. In the n minus 1th term, I have n minus 1 factorial. And then I also have a p raised to the k and a 1 minus p raised to the n minus 1 minus k. After seeing all of that, you should recognize what this is right here. This right here is actually the binomial expansion of p plus 1 minus p raised to the n minus 1 power. Now, if you don't see that trick, I'm going to remind you, if you start doing like a plus b to the n, you're going to start getting the sum. This is just the binomial theorem from k equals 0 to the n of n choose k, a to the n, b to the n minus k. Or sorry, b to the, this first one should say k here. And all we did here to make this slightly different is we just wrote out the definition of n choose k in terms of n minus 1 choose k. And so what I showed is that all of this junk right here, after I factored out the np, is equal to a binomial expansion, and the binomial expansion is the expression p plus 1 minus p. So we're almost done. P plus 1 minus p is actually just 1. And 1 raised to the n minus 1 power, 1 raised to the n minus 1 power is just equal to 1. So it turns out to be proved that our expected value is just np, which is like what I said was the intuitive value of the expression. A really similar proof works for the variance. There's just a little bit more action going on. So I encourage you to try to work on that, and then let me know if you need any help.